All right, this video is for lesson 3 in unit 9. This day in class we spent constructing what is called the unit circle. Now if you miss class, you probably will never get a chance to do that. And I feel really sad for you. I'm going to talk about just sort of the basics of it, but I'm not going to go through the whole construction. If you want to construct one and you were absent, you can come in and I'll work with you on it. But it was just your loss to not be in class. Okay, so this is a circle, and I've identified one point on the circle, the point 1, 0. You can see over here. Well, this is a circle, and its center right here is at the origin. Well, if we're writing the equation of a circle, it usually looks something like this. Well, that should be a y. Well, for our little circle, the center is at the origin, so the center is located at the point 0, 0. That HK is the center of the circle. And the radius of the circle, which would be from the center to the edge of the circle, is a radius of 1. So if we write the equation of this particular circle, x minus 0 is just x. So we have the equation x squared plus, well, y minus 0 is just y, so y squared equals, and if the radius is 1, 1 squared is 1. So the equation of this circle on this paper here, or the board here, is x squared plus y squared equals 1. This is called a unit circle because it is a circle with a radius that has a length of 1 unit. Well, there's quite a few intercepts here. We have marked the location of one intercept. We could mark all of the intercepts. This would be the point 0 over 0 up 1. This would be the point -1, 0. And this would be the point 0, -1. Well, there's a lot more points here. There's a point here on the circle edge. There's a point here. There's a point here. There's a point here. There's actually an infinite number of points along the edge of this circle. And we're going to talk about a specific set of those points that has value in mathematics. But for now, let's talk about some angles, and we'll find some more points in a second. So if I rotate to here, you all know that in degree measure that would be 90 degrees. And if we rotate it all the way over here, a half rotation, that would be 180 degrees. And if we rotate it all the way down to here, that would be 270 degrees. And if we made it all the way around the circle, that would be 360 degrees, 0 to start with. So there's some of the angles that we could rotate on this circle. We could have rotated in radian measure instead of in degree measure though. So let's do it also in radian measure. Half a rotation in radian measure would be, hopefully you remember, pi. And that means if I only go to here, that would be half of pi, which we usually write as pi over 2. If I go down to this one, remember that we've got that 1 pi and we're adding another half. So it's like 1 1/2 pi, but in math we like to write that as 3 pi over 2. So 3/2 is the same as 1 1/2. And if we go all the way around our circle in radian measure, that would be 2 pi. So you can see as I'm marking these angles, the inside of the circle starts to get really busy, and it's hard to measure your angles in the center there if you're looking at more than one angle at a time. So one thing that people like to do when they're looking at a unit circle with all these angles is to write the angles down around the edge. And when you see an angle like pi over 2 here by this line, you know that it's talking about the angle to get to that terminal side. We're going to use that idea. Okay, so we've got the first 4 points that we were interested in on this unit circle, and we in class then found some more points on the unit circle. I'm going to go through a couple of them, not the whole thing, and then I'll skip ahead. So the first angle that we might be interested in, it's a very common angle, it's related to our special right triangles if you remember those, is a 30-degree angle. Well, if I measure a 30-degree angle with a protractor or something, it looks about like this. That's about a 30-degree angle. Well, here, this 30-degree angle has this point right here on the terminal side of that angle. That point is where the terminal side of the angle 30 degrees intersects the unit circle. So I'm going to write the degree measure out here, 30 degrees. And in radians, if you think back to, you could think of it as converting if you want, times it by pi over 180. Or if you wanted to just remember that pi is half a rotation, 30 happens to be 1/6 of that, so it's pi over 6 in radians. So let's find the coordinates of this point. Well, I'm going to erase, whoa, I didn't mean to erase the whole thing, but that's okay. Sorry. Well, we could construct, oops, right here, a triangle. In fact, we've constructed such triangles before. We called them reference triangles. So if we construct this little reference triangle here, this reference triangle happens to be, because we measured this angle and we know that it's 30 degrees, this happens to be a 30, 60, 90 triangle. Well, we have looked at 30, 60, 90 triangles before, and you know that they have a special relationship in their sides that can make it easy to find different side lengths, and it's whatever the short leg is. You can double it to get the hypotenuse, and you can multiply that to get by √3 to get the longer leg. Well, we have a special right triangle here, but the side that we happen to know is this. We know this hypotenuse length. Well, the reason we know the length of the hypotenuse is because the hypotenuse happens to be a radius of the circle. So we know that hypotenuse is length 1. And if the hypotenuse is length 1, well, that means this short leg right here must be 1/2. So we know that whatever that short leg is, the hypotenuse is double it. So we have the hypotenuse is 1, the short leg is 1/2, and to get the length of the longer leg, you take that short leg and you multiply it by √3. Well, a more common way to write 1/2 times √3 would be √3 over 2. And this would be that final leg of the triangle. Well, look at this point on this terminal side of the circle. If I want them to know the location or the coordinates of this point, it looks like I go over by the long leg, the length of the long leg. So the first part of this coordinate is going to be that I've gone over √3 over 2. And then it looks like I'm going up by the length of the short leg. So that's going to be 1/2. So the coordinates of that point on the edge of the circle is √3 over 2, 1/2. Well, in class, we then reflected that around and we created another triangle over here. This time, it had a 30-degree angle here, but then we knew that meant we were talking about the angle 150 degrees. And in radian measure, that's the same as 5 pi over 6. And this time the coordinates of this point, well, they're very similar. It's the same, it's a congruent triangle. They have the same side lengths. It's just that this time you're going back by root 3 over 2, so negative root 3 over 2, and you're still going up 1/2. Well, you can reflect those triangles again and form 2 more triangles. And we're making kind of a bow tie here. Remember, the reference triangles are usually forming a bow tie shape if you've got lots of them. Okay, so you could find these additional coordinates and their angle measure and their coordinates. So I'm going to go to the next type of triangle. 45, 45, 90 triangle is the next one we studied as one of our special right triangles. Well, if we draw a 45-degree angle here, in radian measure, that's pi over 4. And if we wanted to know the coordinates of this point, we could think about a 45, 45, 90 triangle. If we know the hypotenuse, which we do because it's a radius of the circle, it has length 1. If you remember the relationship in a 45, 45, 90 triangle, it's that the hypotenuse is the square root of 2 times as long as the leg. So if you're figuring out the leg from the hypotenuse, you have to divide by root 2. And if we rationalize that, we find that the length of the leg is root 2 over 2. It's a 45, 45, 90 triangle. It's isosceles, so both legs are the same. So if we wanted to find this point on the edge of the circle, this point here, it would be that we have to go over by the length of the leg, square root of 2 over 2, and we have to go up by the length of that leg, root 2 over 2. So we have another point. And again, we could reflect that around to all of these different quadrants. Oops. And we could label them, and we did in class. And then there's one last angle from our special right triangles, and that's the 60-degree angle. Well, the 60-degree angle puts us about, let's see, about right here. If we're measuring with a protractor, we could get that exactly right. And again, you know, it's actually this same 30, 60, 90 triangle. It's just that it's a tall, it's just rotated a little or reflected. So again, the hypotenuse is 1. That means this short leg has got to be half, and this longer leg is root 3 over 2. So if I'm writing the coordinates of this point here on the edge, it would be that we've gone over 1/2, and we're going up by the length of the long leg, root 3 over 2. And that was a 60-degree angle in radian measure. That's the same as pi over 3. And again, we reflected that around. And we did all this work to create all these triangles. And basically, this unit circle is creating for us a set of reference triangles that we can use to help identify the sine, cosine, and tangent of various angles. When you finish constructing your unit circle, it should look something like this. And I know the green is a little bit hard to see. But it'll have all of the angles on it, and you can actually even get a printed version of this that's a little bit easier to read than a handmade version. But it's really valuable to make a handmade one. It really helps you to understand the symmetries and things. So I'm going to go over 6 questions on sort of how to use this unit circle, and then we'll actually continue working with the unit circle and learning more about the unit circle next time in class. So the first question is, what is the exact value of the sine of 135 degrees? So I have one of the quadrants from the unit circle up here. I just picked one so we could see it a little better. But if you're answering a question like this, the sine of 135 degrees, you find that angle on your unit circle. 135 degrees happens to be here. And if you want to know the sine, you can use this reference triangle right here to help you figure out the sine of that angle. And we're going to use this reference angle here. So the sine of an angle is the opposite over the hypotenuse. So in this case, from the perspective of my reference angle here by the origin, the opposite side is how far up it went. So that's the y coordinate, root 2 over 2 in this case. And I need to divide by the hypotenuse. Well, the hypotenuse happens to be the radius of the circle. So the hypotenuse has length 1. And you can see why it might be a little powerful to have a circle with radius 1. Since that hypotenuse is 1, dividing by 1 is super easy. It must simply be root 2 over 2. Let's look at another sine. This one is the sine of pi over 6. So this is in radians. Well, pi over 6 happens to be this angle. It's the same as 30 degrees. Pi over 6 is right here in quadrant 1. So if I want to know the sine of pi over 6, well, sine is the same as opposite over hypotenuse. We're using this reference angle to help us. So here's my opposite side, and here's my hypotenuse. The hypotenuse is the radius of the circle, so it's 1. The opposite side of the triangle is how far up it went, so that is 1/2. 1/2 over hypotenuse is 1. 1/2 divided by 1 is just 1/2. So we have now found the sine of pi over 6. Let's try a couple of cosines. Cosines are the ratio of the adjacent to the hypotenuse. So we're going to look for some adjacent sides this time. First one is the cosine of 240 degrees. 240 degrees is kind of hard to see, but 240 degrees is down here in green. So we're looking to use this reference triangle here. Well, from the perspective of our reference angle, this right here is the adjacent side, how far over it went. Well, that's the x-coordinate here. That's negative 1/2. The adjacent side is negative 1/2. And cosine relates the adjacent to the hypotenuse. Well, the hypotenuse is the radius of the circle. The hypotenuse has length 1. So the cosine of 240 degrees is negative 1/2 divided by 1, which is just negative 1/2. Let's try a cosine in radian measure. So the radian measure we want to look at here is 7 pi over 4. 7 pi over 4 is in the 4th quadrant. And as you're working with the unit circle, you'll get more and more comfortable with where these different angles are. At first, you may have to search a bit as you're looking. So 7 pi over 4 is here. We're going to use some information from this point here. So the cosine is the adjacent over hypotenuse. We're using this reference triangle. The adjacent side is here. Here's my reference angle. Adjacent side is here. It's telling me how far over I went. That's this coordinate. Root 2 over 2 tells me how far over I went. And I want to divide by the hypotenuse. Well, the hypotenuse is the radius of the circle. It has length 1. So the cosine of 7 pi over 4 is root 2 over 2 divided by 1, which is just root 2 over 2. We love to divide by 1. Okay, we're going to look at some tangents now. Tangents are quite a bit trickier for a lot of people because they don't involve the hypotenuse. Tangent is the ratio of the opposite over the adjacent. The first one we're looking at is 225 degrees. That is located right here. So 225 degrees, we're going to use these two coordinates. So if you think about your reference triangle, and here's the reference angle, the adjacent side is here. That's how far back you went. So that's a negative root 2 over 2. And the opposite is here. In this case, it's telling me how far down I went. And it's also a negative root 2 over 2. So if I write my ratio, tangent 225 degrees equals, the opposite side was negative root 2 over 2. The adjacent side was negative root 2 over 2. Well, if I have something, maybe that something is a negative root 2 over 2, and it's divided by itself, negative root 2 over 2, they're the same. Anything divided by itself is equal to 1. So tangent of 225 degrees is equal to 1. Last one, we're looking for the exact value of the tangent of 11 pi over 6. It's located in the fourth quadrant. Here it is, 11 pi over 6. We're going to use this blue reference triangle to help us. Well, tangent is the ratio of the opposite over the adjacent. Well, the opposite side of this triangle from the perspective of our reference angle here would be this side, and it happens to be negative 1/2. And we're going to divide by the adjacent side of our triangle. That's right here. And it happens to be that we went over root 3 over 2. Now this is a compound fraction, and it can be really tricky for people to simplify and figure out how to get the value of that. In math, if I'm having a hard time simplifying, sometimes I like to try multiplying by a fancy number 1. The fancy number 1 I'm going to multiply by right now is the number 2 divided by 2. That's a really fancy number 1. Well, if I do that fancy number 1, this 2 and this 2 reduce, and this 2 and this 2 reduce. So I'm left with a negative 1 over root 3. And I could, to be more proper, rationalize that. It's not incorrect at this point, but we consider it more simple and in better form if we rationalize it. So the tangent of 11 pi over 6 is equal to negative root 3 over 3. The tangents are definitely a little bit trickier than the other two ratios, sine and cosine. And it's really because of the hypotenuse being 1. Okay, so that's your homework is in part to practice using these reference triangles, and then a lot of your homework, more of your homework is on reviewing the other concepts like arc length, converting angles, sketching radian measures. So if you need some help, come in and talk with me and we'll try to get you up to speed before the test. The test is going to be next week. For B Day it will be on Thursday, and for A Day it will be on Friday, March 10th. That's it for this lesson.